What if everything we've ever seen, every star, every galaxy, every shimmering speck of light in the night sky, is just a whisper of the true vastness that lies beyond? Picture this: the observable universe, the part we can detect with our most powerful telescopes, stretches an astonishing 93 billion light-years across. But here's the twist: that's not the edge of reality. It's just the edge of what light has had time to reach us since the dawn of time. Imagine standing on the shore of an endless ocean, where the horizon is not the limit of the water, but the limit of your vision. That's the universe we live in, a cosmos that likely stretches far beyond the boundaries of our perception, hiding secrets we've only begun to unravel. This isn't just about distance or scale, it's about the very nature of existence. The so-called edge of the observable universe isn't a physical wall or a cosmic barrier. It's a frontier of time, a line drawn by the speed of light and the age of the universe itself. Beyond that line, galaxies might be swirling, stars might be burning, and entire civilizations could rise and fall, all invisible to us, not because they don't exist, but because their light hasn't had time to cross the unimaginable gulf between us and them. It's a humbling thought. We're not at the center of everything. We're just in a pocket of visibility, peering out into a darkness that might never fully lift. And that's where the real mystery begins. What lies beyond that edge? Is the universe infinite, stretching forever into the unknown? Or does it curve back on itself in ways we can't yet fathom? These questions don't just challenge our understanding of space, they shake the foundations of how we see ourselves in the grand scheme of things. Today, we're going on a journey to explore these cosmic enigmas, to question what we think we know, and to confront the mind-bending possibility that the universe is far stranger, far larger, and far more mysterious than we've ever dared to imagine. Buckle up, because by the end of this, the night sky will never look the same to you again. To understand the limits of what we can see, let's break down what the observable universe really means. Picture a giant bubble centered around Earth, stretching 46.5 billion light-years in every direction. That bubble contains every star, every galaxy, every flicker of radiation we've ever detected. Everything light has had time to reach us in the 13.8 billion years since the Big Bang. But here's the catch: that doesn't mean the universe stops there. It just means we're seeing as far as the cosmic speed limit, the speed of light, allows. Think of it like sitting in a boat on a foggy morning. The horizon isn't the edge of the ocean. It's just the farthest point you can see before the curve of the Earth and the thickness of the air obscure what's beyond. The observable universe works the same way. It's not a boundary of space, but a boundary of time and perception. Now, here's where things get even more fascinating. The entire universe, the totality of everything that exists, could be infinitely larger than what we observe, or it might curve back on itself like the surface of a balloon, making it finite but without an edge. We simply don't know. What we do know is that every second, as light from farther away finally reaches us, that cosmic horizon expands slightly. Galaxies that were once invisible suddenly flicker into view, pushing the boundary of our knowledge just a little farther. But no matter how powerful our telescopes become, there will always be regions of space whose light hasn't had enough time to reach us and may never will. So when we talk about the edge of the observable universe, we're really talking about the limits of our own cosmic perspective. It's a reminder that the universe doesn't revolve around us. We're just one small witness to an unfolding story much grander than we can fully grasp. And that raises the most thrilling question of all. If the observable universe is this unimaginably vast, what lies in the darkness beyond? the idea that the observable universe has a definitive edge is one of the most persistent misunderstandings about our cosmos. It's easy to picture it as a giant sphere with some kind of barrier at the outer limit, like a cosmic version of the old maps that warned, "Here be dragons." But the truth is far more subtle and far more fascinating. What we call the edge isn't a physical boundary at all. It's more like the edge of a spotlight's beam, the furthest point where light has had enough time to travel to us since the beginning of the universe. And just like that spotlight, the beam keeps growing, revealing more of what was always there but hidden in darkness. At the very limit of what we can observe lies the cosmic microwave background, or CMB, the faint afterglow of the Big Bang itself. This isn't a wall or a barrier. It's a time capsule, a snapshot of the universe when it was just 380,000 years old, finally cool enough for light to break free and travel across space. When we detect the CMB, we're not hitting some cosmic dead end, we're peering back into the universe's infancy, seeing the afterimage of its fiery birth. And just as a baby photo doesn't define the limits of a person's life, the CMB doesn't mark the end of the universe. It marks the beginning of our ability to see it. Here's the mind-bending part. Every second that boundary shifts. As light from regions even farther away finally reaches us, our cosmic horizon expands. It's like standing in a dense fog that slowly lifts over centuries, revealing more and more of the landscape that was there all along. Some of the galaxies we see today were once beyond our observational limits, their light only now arriving after an epic journey across space and time. And yet, no matter how long we wait, there will always be regions so distant that their light hasn't had time to reach us, and may never will, thanks to the accelerating expansion of the universe. So if the observable universe isn't truly the end of anything, what does that mean for the bigger picture? Could there be galaxies, stars, even entire civilizations so far beyond our view that we'll never know they exist? Or does the universe repeat itself in some vast, intricate pattern, making our observable bubble just one tile in an infinite cosmic mosaic? These aren't just abstract questions, they force us to confront the staggering possibility that everything we've ever seen, everything we've ever known, might be just the tiniest fraction of what's really out there. Imagine blowing up a balloon with tiny dots scattered across its surface. As you inflate it, the dots move farther apart, not because they're traveling across the balloon, but because the space between them stretches. Now picture that balloon expanding faster and faster, some dots speeding away so quickly that their light can never catch up to you. That's precisely what's happening to our universe on a cosmic scale. Space itself isn't just growing, it's accelerating, stretching the fabric of reality so dramatically that distant galaxies are being dragged beyond the horizon of our perception. This acceleration comes from a mysterious force we call dark energy, an invisible pressure woven into the cosmos that pushes space apart like an unstoppable tide. The more the universe expands, the stronger dark energy's grip becomes, creating a runaway effect that's forever altering our cosmic landscape. Right now, there's a critical boundary called the Hubble volume, a spherical region where space expands slower than the speed of light. Anything inside this bubble can still send photons our way, but galaxies beyond it are receding so fast that their light is fighting a losing battle against the stretching void. They haven't vanished, they've simply been outpaced by the expansion of space itself, like a runner on a treadmill that keeps speeding up until their strides can't keep them in place. Here's where it gets haunting. Every second, more galaxies cross that threshold, disappearing from our view not in a blaze of glory but in silence, their light stretched into wavelengths so long and faint they dissolve into the cosmic background. It's as if the universe is erasing itself from our observation, one star system at a time. And this isn't some distant future scenario, it's happening right now. The Milky Way, along with our local group of galaxies, will one day be an isolated island in a sea of darkness, every other cluster of stars too far away for their light to ever reach us again. Yet this relentless expansion hints at something extraordinary. The universe we see may be just a speck in an unfathomably larger reality. If space is stretching this aggressively, what does that suggest about the regions already beyond our Hubble volume? Could there be countless other galaxies, structures, even forms of life receding into the distance, forever unknowable? The acceleration we observe might be the strongest clue yet that the true scale of existence dwarfs even our wildest estimates, a cosmos so vast that the observable universe, for all its grandeur, is merely the first page of an endless story. The most radical clue about what lies beyond our observable horizon comes from a theory so powerful it reshaped cosmology: inflation. Picture the universe in its first sliver of existence, a trillionth of a second old. Suddenly, space didn't just expand, it exploded outward faster than the speed of light, doubling in size over and over again in intervals so brief they're almost impossible to fathom. In less time than it takes to blink, a speck smaller than an atom became a volume trillions of times larger than our current observable universe. And here's the staggering implication. If inflation happened, and the evidence strongly suggests it did, then the cosmos we can see is just one bubble in a froth of reality, with countless other regions stretched so far beyond our horizon they might as well be separate universes. This isn't science fiction. The echoes of inflation are written in the cosmic microwave background, the faint glow from the early universe. Those subtle temperature variations, the blueprint for galaxies and voids we see today, were likely sculpted by quantum fluctuations during inflation, tiny ripples magnified to cosmic proportions as space stretched. Think of it like blowing up a balloon covered in microscopic dust. As the balloon inflates, those tiny specks become vast continents. Inflation did the same to quantum jitters, stretching them into the seeds of superclusters and the voids between them. But here's where it gets even wilder. If inflation never stopped, if it's eternal, then our entire observable universe might be just one pocket in an endless multiverse, with other bubbles forever out of reach. Some could have entirely different laws of physics, different dimensions, even different versions of time. We'll never see them, never interact with them, but their existence would mean the true scale of reality is so vast it makes our 93 billion light-year horizon seem smaller than a grain of sand on an endless beach. So how do we even begin to study what we can't observe? The answer lies in the fingerprints inflation left behind. The uniformity of the cosmic microwave background, the way galaxies cluster on colossal scales, these are clues written in the fabric of space itself. By studying the patterns in the universe we can see, we're reverse engineering the physics of the unseeable, like detectives reconstructing a crime scene from a single speck of dust. Every measurement, every simulation brings us closer to answering the ultimate question. Is our universe just one note in an infinite cosmic symphony, or is there something even stranger waiting beyond the edge of our perception? The cosmic microwave background isn't just a relic of the Big Bang. It's a treasure map hiding clues about the universe's true scale. When we examine this faint glow, one detail stands out: its staggering uniformity. No matter which direction we look, the temperature of the CMB varies by less than 100,000th of a degree. That near-perfect symmetry is bizarre because, according to the laws of physics, regions of the early universe too far apart to have ever interacted should show wild differences. So how did they sync up? The answer lies in inflation, that explosive faster than light expansion in the universe's first moments. It stretched a tiny, homogeneous patch of space into a volume so vast that even the farthest reaches of our observable universe were once neighbors, explaining why they share the same temperature today. But here's the catch: if inflation could smooth out a region this big, the total universe must be unimaginably larger, like a single tile in a mosaic spanning entire galaxies. This leads us to the flatness problem, another puzzle etched into the CMB. The geometry of our universe appears almost perfectly flat, meaning parallel lines stay parallel forever, rather than curving or diverging over cosmic distances. But for space to be this flat, the early universe must have been fine-tuned to an absurdly precise density. Inflation solves this by stretching space so drastically that any initial curvature becomes imperceptible, like blowing up a balloon to the size of Earth until its surface feels flat beneath your feet. The CMB's flatness isn't just a curiosity, it's a smoking gun, hinting that the universe extends far beyond our observational limits, with our 93 billion light-year bubble merely a speck in a grander, possibly infinite expanse. Zoom in closer on the CMB, though, and you'll find tiny ripples, slight temperature variations that map the seeds of future galaxies. These fluctuations, magnified by inflation, reveal a pattern so vast that some structures appear to span distances larger than our observable horizon. How can something be bigger than the universe we see? It's another clue that we're glimpsing only a fragment of reality, like hearing a single note of a symphony and trying to guess the entire composition. Those ripples suggest connections, regions that were once united before inflation tore them apart, leaving echoes of their shared origin in the cosmic background. So what does this mean for the bigger picture? If the CMB's uniformity, flatness, and ripple patterns all point to a universe far larger than we can observe, what other evidence might be hiding in plain sight? Could the very laws of physics we take for granted be just local bylaws in an endless cosmic tapestry? The answers might lie in the next frontier, the mysterious forces shaping the universe's accelerating expansion. When astronomers began mapping the universe in 3 dimensions, they didn't just find galaxies scattered randomly. They uncovered an intricate cosmic web, a vast network of threads and voids stretching across billions of light years. These filaments of galaxies, separated by enormous empty spaces, form a pattern so colossal that some structures seem to defy the very limits of our observable universe. Take the Hercules Corona Borealis Great Wall, for instance, a galaxy cluster so immense it spans 10 billion light-years, a structure that shouldn't exist if the cosmos ended at our horizon. How can something be larger than the universe we see? The answer lies in the eerie uniformity of the cosmic web, a pattern that doesn't stop at the edge of our perception but hints at a reality extending far beyond. Projects like the Sloan Digital Sky Survey have revolutionized our understanding by meticulously charting millions of galaxies, revealing how these filaments and voids weave together like threads in a tapestry. But here's the catch: the patterns they've uncovered are so vast and consistent that they couldn't have formed in isolation. The cosmic web structure suggests a continuation, as if we're seeing just one small section of a design that stretches into the unobservable darkness. Imagine looking at a single tile of an endless mosaic. The repeating patterns tell you there's more beyond the edges, even if you can't see it. This raises a profound question. If the universe's large-scale structure extends past our observational limits, what does that mean for its true scale? Could the cosmic web be infinite, with filaments and voids repeating forever? Or does it curve back on itself, creating a finite but boundless cosmos? The philosophical implications are staggering. An infinite universe means every possible configuration of matter, every variation of reality, might exist somewhere in the void, alternate Earths, alien civilizations, even copies of ourselves staring back at a different cosmic horizon. It's a humbling reminder that our corner of existence, for all its grandeur, might be just one whisper in an endless conversation. As we push the boundaries of observation, each new galaxy survey peels back another layer of the cosmic mystery, revealing not just where we are, but how much we've yet to discover. The universe's structure isn't just a map of what we know, it's a signpost pointing to the unfathomable unknown. What if our universe isn't the only one? Imagine a frothing ocean where every rising bubble is its own self-contained world, each with its own rules, its own physics, its own destiny. This isn't just poetic imagery, it's the multiverse hypothesis, the idea that our observable universe might be just one bubble in an endless cosmic foam, with countless others floating alongside it, forever beyond our reach. The theory springs from eternal inflation, that mind-bending moment when the early universe expanded faster than light, stretching space so violently that pockets of it pinched off into separate domains. Some of these bubbles might have laws of physics wildly different from ours. Gravity could be weaker, light might move slower, or atoms might never have formed at all. Others could be nearly identical with only subtle variations. And in this infinite sea of possibilities, it's no surprise that at least one bubble ours ended up with the perfect recipe for stars, planets, and life. This isn't just speculation. The fine-tuning of our universe has long puzzled scientists. Why do the fundamental constants, the strength of gravity, the mass of an electron, the energy in empty space, have such precise values that even slight changes would make life impossible? The multiverse offers a compelling answer. If infinite universes exist, each with random physical laws, then statistically, some must hit the cosmic jackpot. We're not special, we're just the lucky ones who ended up in a bubble where everything clicked. Think of it like a cosmic lottery with trillions of tickets, and ours happens to be the one that allows galaxies to form and chemistry to unfold. But how could we ever test something so seemingly untestable? The clues might lie in the cosmic microwave background. If our universe collided with another bubble in the distant past, the shockwave could have left scars in the CMB's temperature patterns, subtle bruises in the fabric of space. Some researchers have even claimed to spot these anomalies, though the evidence remains controversial. Another approach involves studying the distribution of dark energy. If its strength varies across the multiverse, our local value might be a clue to what's happening beyond our horizon. The multiverse hypothesis forces us to confront a humbling truth. The limits of our observation might not just be practical, they could be existential. If other universes are forever cut off from us by the speed of light and the relentless expansion of space, we may never know for sure if they're out there. But the very possibility reshapes how we see our place in the cosmos. No longer the center of everything, we're just one flickering light in an unimaginably vast labyrinth of realities. And that raises an even deeper question. If the multiverse is real, what other wonders or horrors might be hidden in the bubbles beyond? Our understanding of the universe is built on a simple, profound limitation. We can only study what we can detect. And for most of human history, that detection has been shackled to light. Every star map, every galaxy catalog, every breathtaking Hubble image is just a slice of reality filtered through the narrow window of the electromagnetic spectrum. But what if there's so much more happening in the darkness, in the silence, in the spaces between? Take neutrinos, for example, ghostly particles so indifferent to matter that trillions pass through your body every second without a single collision. These cosmic messengers carry information from the hearts of collapsing stars, the cores of distant galaxies, even the violent aftermath of the Big Bang itself. Unlike light, which can be absorbed or scattered by cosmic dust, neutrinos travel unimpeded across the universe, offering a backstage pass to events our telescopes will never see. The problem, they're maddeningly difficult to catch. Detectors like Ice Cube, buried deep in Antarctic ice, wait years to capture a handful of these phantoms. But imagine a future where neutrino telescopes become as routine as optical ones suddenly. The universe wouldn't just be something we see. It would be something we feel, its hidden rhythms pulsing through detectors like a heartbeat in the dark. Then there are gravitational waves, ripples in spacetime itself, sent racing across the cosmos by colliding black holes and neutron stars. These distortions aren't light or matter or anything bound by the electromagnetic spectrum. They're the very fabric of reality, ringing like a bell, carrying stories of collisions so ancient their light has long since faded beyond our reach. When LIGO first detected gravitational waves in 2015, it didn't just confirm Einstein's prediction, it opened a door to an entirely new way of observing the universe. Now, imagine combining these signals with neutrino data and traditional astronomy. Suddenly, we're not just looking at the universe, we're listening to it, piecing together a symphony where light was only ever one instrument. But here's the humbling truth, even these cutting-edge tools have limits. Gravitational waves weaken with distance, neutrinos remain elusive, and some corners of the cosmos might be so alien they emit no signal we currently recognize. That's where mathematics becomes our most powerful telescope. Equations can peer beyond the observational horizon, predicting the behavior of dark matter, the nature of singularities, even the possibility of higher dimensions. When observations fall short, theory bridges the gap, sketching blueprints of realities we can't yet touch. It's like navigating a pitch-black room using only a map you've drawn from echoes imperfect but transformative. The lesson is clear: to truly grasp the universe, we can't rely on light alone. We need every lens, every frequency, every whisper of data the cosmos offers. Because the greatest discoveries often lie not in what we observe, but in what we've yet to learn how to see. Mathematics isn't just a human invention, it's the universe's secret language, a tool so precise it lets us map realms we'll never physically reach. Think of it like echolocation. Just as a bat navigates the dark by interpreting echoes, we use equations to reconstruct the cosmos beyond our observational limits. Take the Friedmann models, for instance. These deceptively simple formulas, born from Einstein's general relativity, describe how space itself can curve, twist, or stretch over time. They reveal three possible shapes for the universe: flat like a sheet of paper, closed like a sphere, or open like a saddle. The mind-bending part: each shape implies a radically different fate for reality, from eternal expansion to eventual collapse, and yet all three are solutions to the same equation. Symmetry plays an equally profound role. The universe adores patterns, from the spiral arms of galaxies to the hexagonal storms on Jupiter. Mathematics uncovers these hidden regularities, acting like a cosmic X-ray to peer through the noise. When physicists study the symmetries of particle physics or the geometry of space-time, they're not just describing what we see, they're reverse engineering the scaffolding of existence. It's how we deduced inflation's existence long before we found its fingerprints in the cosmic microwave background. The equations predicted the phenomenon, like a detective solving a case from a single fingerprint. Topology, the study of shapes and their connections, takes this even further. Imagine the universe as a piece of paper. If you glue the edges together, you get a torus, a donut shape where traveling far enough in one direction brings you back where you started. Now scale that up. Could the entire cosmos have similar hidden loops, making it finite yet boundless? Topology doesn't just suggest possibilities, it calculates their consequences. For example, if the universe were a giant hypersphere, distant galaxies would appear in multiple places in the sky, like reflections in a funhouse mirror. We haven't found such duplicates yet, but the math keeps the door open to wonders we've yet to imagine. Here's where it gets even stranger. Dark energy, the mysterious force accelerating the universe's expansion, was first glimpsed not through a telescope but through equations. The numbers insisted something was missing, a cosmic tension pulling space apart, and only later did supernova observations confirm it. Mathematics doesn't just describe reality, it anticipates it, like a compass pointing to uncharted territories. And if our models are this powerful within the observable universe, what might they reveal about the vast unknown beyond? Which leads us to the ultimate question: what lies in the voids past our horizon? Is it more of the same, endless galaxies and stars? Or does the universe give way to true nothingness, a void so complete it defies even mathematics? The equations hint at possibilities, but the answers may forever linger just out of reach, like shadows on the cave wall of our cosmic prison. Beyond the edge of our observable universe lies not just more space, but the potential for realities so alien they defy imagination. Picture an infinite expanse where familiar laws of physics crumble, where matter arranges itself into structures beyond galaxies, beyond superclusters, into formations so vast they make the cosmic web look like a child's scribble. Some theories suggest these regions could harbor domain walls, cosmic fault lines where the very fabric of reality shifts, creating abrupt transitions between universes with different fundamental constants. Imagine stepping across an invisible threshold where gravity suddenly weakens, light slows to a crawl, or time itself flows backward. These aren't just hypothetical playgrounds for physicists. They're genuine possibilities in a cosmos where inflation stretched quantum fluctuations into entire alternate realities. Then there's the chilling paradox of the Boltzmann brain, a thought experiment born from the chaos of infinity. In an eternal, randomly fluctuating universe, the odds dictate that over unfathomable timescales, a self-aware consciousness could spontaneously assemble from stray particles, complete with false memories of a life it never lived. This disembodied observer would exist for just a fleeting moment before dissolving back into the void, convinced it had experienced a full existence. The unsettling implication: in an infinite reality, there might be countless such phantom minds, each believing itself to be the only real entity in a sea of illusion. Are we any different? Could our entire universe, with its 13.8 billion years of history, be nothing more than a random fluctuation in the quantum foam? The math allows it, though most scientists dismiss it as a philosophical nightmare rather than a physical likelihood. Not all models paint such a lonely picture. The island universe hypothesis offers a counterpoint: the idea that our cosmos is a self-contained bubble, floating in an eternal void with nothing beyond its boundaries. In this scenario, the universe isn't infinite. It's a finite oasis where the Big Bang marked both the beginning of space and the edge of existence. No alternate realities, no Boltzmann brains, just our solitary cosmic island expanding into emptiness. It's a comforting thought in some ways, but it raises its own paradoxes. What then lies outside the island? True nothingness, a void so absolute that even the concept of outside becomes meaningless. Time adds another layer of mystery. Even if other regions exist beyond our horizon, the accelerating expansion of space means their light will never reach us. They're not just distant, they're perpetually receding, locked forever behind a curtain of expanding darkness. In a sense, the universe is building its own prison walls, brick by brick, as more and more of reality slips beyond the reach of observation. Yet time's arrow might not point the same way everywhere. Some theories suggest other domains could experience time flowing backward or in loops, making causality as fluid as the cosmic tides. So where does that leave us, staring into the abyss, armed with equations and imagination, knowing that the true nature of reality might forever elude our grasp? Whether we're one bubble in a frothing multiverse, a fleeting fluctuation in an eternal void, or the sole inhabitants of a self-contained cosmos, one truth remains: the universe is far stranger than we've dared to dream. And perhaps that's the most exhilarating revelation of all: the recognition that the unknown isn't a barrier, but an invitation to keep exploring. Time doesn't just move forward in the cosmos, it stretches outward, weaving the very fabric of what we can see. Every photon that reaches our telescopes is a messenger from the past, carrying stories written billions of years ago. When we gaze at the Andromeda galaxy, we're not seeing it as it is today, but as it existed 2.5 million years in the past, a snapshot from when early humans were just discovering fire. Push farther out, and the light from the most distant galaxies shows them as they were mere hundreds of millions of years after the Big Bang, their newborn stars flickering in the cosmic dawn. The edge of our observable universe isn't just a spatial boundary, it's a time capsule, a limit set by how long light has had to travel across the expanding void. But here's the twist: that horizon isn't fixed. As the universe ages, light from even more distant regions will finally arrive, revealing galaxies that are currently invisible to us. You'd think this means our cosmic view will keep growing forever, but dark energy has other plans. Because space itself is stretching faster and faster, there's a critical threshold called the future visibility limit, the farthest point whose light will ever reach us. Beyond that, galaxies are receding so quickly that their light, no matter how long it travels, will never overcome the expansion of space. It's like trying to run up a descending escalator that keeps speeding up. Eventually, even the fastest runner can't make progress. For us, that limit lies about 60 billion light-years away, meaning whole swaths of the universe, though they exist right now, are already destined to remain forever hidden. This makes our current cosmic era astonishingly special. We live in a brief sliver of time when the afterglow of the Big Bang is still detectable, when the universe is transparent enough to see its large-scale structure, and when countless galaxies remain within observational reach. Civilizations born billions of years from now will inherit a far lonelier cosmos. The accelerating expansion will have dragged most galaxies beyond their visible horizon, leaving only a handful of nearby stars in an otherwise empty sky. The cosmic microwave background will have redshifted into invisibility, erasing the last traces of the universe's fiery birth. Future astronomers might never know other galaxies existed at all, their telescopes peering into a darkness we'd recognize as profoundly incomplete. Think of it like standing in a library where the books are slowly turning to dust. Right now, we can still read many of them, the light from distant galaxies, the whispers of the early universe. But with each passing moment, more volumes crumble beyond recovery, their stories lost to the void. We're uniquely positioned to glimpse the cosmos at its most generous, its grand narrative still partially legible. Which raises a haunting question: if our observable universe is just a shrinking window into deeper time, does the cosmos even have an end? Or is reality an infinite Matryoshka doll of horizons, each civilization trapped inside its own pocket of perception, forever wondering what lies beyond? Is the universe infinite, or does it have an edge? This question isn't just about scale, it's about the fundamental nature of reality. The cosmic microwave background offers our strongest clues. Its near-perfect flatness suggests space could stretch endlessly, like an infinite sheet of paper. But flatness alone isn't proof. Imagine blowing up a balloon. The larger it gets, the flatter any small patch appears. Our observable universe might just be one tiny, seemingly flat region in a cosmos that's far grander and possibly finite. Theoretical models amplify this mystery. Eternal inflation paints a picture of countless bubble universes sprouting from an endlessly expanding quantum foam, each with its own physics. In this scenario, infinity isn't just possible, it's inevitable. Yet infinity breaks our intuition. If space truly has no end, then somewhere out there, every possible arrangement of particles must repeat. There could be infinite copies of Earth, infinite versions of you reading infinite variations of this sentence. The idea is dizzying but mathematically plausible. Dark energy complicates things further. The universe isn't just expanding, it's accelerating, pushing galaxies beyond our horizon faster than their light can reach us. Over time, even nearby clusters will vanish into the void. This creates a paradox, an infinite universe where almost all of it becomes permanently invisible, leaving us isolated in an ever-shrinking island of visibility. Infinity might exist, but we'll never explore it. Then there's the holographic principle, a radical idea suggesting our three-dimensional universe could be encoded on a two-dimensional boundary, like a cosmic DVD. If true, the edge of the universe wouldn't be a place but a surface containing all information within. Black holes hint at this possibility. Their event horizons seem to store information about everything they swallow, as if the universe naturally compresses reality into boundaries. Black holes themselves might be microcosms of cosmic limits. Their singularities crush space and time, creating points where physics as we know it ends. Some theories suggest the entire universe could have emerged from a singularity, making black holes both end points and potential gateways to deeper layers of reality. If space-time can curve infinitely inward within a black hole, could the universe also curve outward without end? The answers might lie in the quantum whispers at the edge of these dark behemoths. So is the universe infinite? The evidence leans toward possibly, but the truth might be stranger. Whether finite or endless, one thing is certain: the cosmos refuses to be contained by human imagination. Every answer uncovers deeper questions, every horizon hides another, and the universe, whatever its true size, remains the greatest mystery of all. Black holes aren't just cosmic vacuum cleaners, they're mirrors reflecting the very same mysteries that haunt the edges of our observable universe. Take the event horizon, that invisible boundary where gravity becomes so strong not even light can escape. It's eerily similar to the limit of our cosmic vision. Both mark a point of no return, a threshold beyond which information vanishes from our grasp. Just as we'll never know what lies past the observable universe's horizon, anything crossing a black hole's event horizon is lost to us forever, its secrets crushed into the singularity. But here's where it gets fascinating. Black holes aren't entirely dark. Thanks to quantum mechanics, they emit Hawking radiation, a faint glow that slowly leaks energy into space. This discovery reshaped our understanding of entropy and information, suggesting that even the most destructive forces in the universe might leave faint echoes of what they've consumed. The thermodynamics of black holes offer a startling parallel to the cosmos at large. Just as an event horizon hides a singularity, our observational horizon conceals the true nature of whatever lies beyond. And just as Hawking radiation hints that black holes might preserve information in some scrambled form, the cosmic microwave background might encode clues about regions we can't directly observe. It's as if the universe operates on a principle of partial disclosure, revealing just enough to tantalize, but never the full picture. Picture a one-way mirror. We see reflections of reality, light from distant galaxies, ripples in space-time. but the other side remains forever opaque, its truth slipping through our fingers like smoke. This dance between the seen and unseen forces us to confront a profound question. If black holes can radiate, can the universe itself? Some theories suggest that our cosmic horizon might emit its own version of Hawking radiation, a quantum whisper from the void. If true, it would mean the universe isn't just expanding, it's evaporating at the edges, particle by particle. The implications are staggering. Could the information swallowed by our cosmological horizon someday resurface, like a message in a bottle washing ashore after eons at sea? Or is it lost forever, erased by the relentless stretching of space? Yet amid these grand abstractions, a more intimate mystery lingers. Where does life fit into this vast, veiled cosmos? If the universe is built on horizons, limits to what we can see, know, or touch, what does that mean for our search for meaning, or even other civilizations? Are we, like particles near a black hole's edge, teetering between connection and isolation, forever wondering what lies just beyond the light? If the universe is truly infinite, teeming with countless galaxies, stars, and planets, then where is everyone? This is the haunting heart of the Fermi Paradox, the glaring contradiction between the high probability of extraterrestrial life and our utter lack of evidence for it. In a cosmos so vast that even conservative estimates suggest billions of potentially habitable worlds, silence feels deafening. The sheer scale of existence should make civilizations as common as grains of sand on a beach, yet our radios and telescopes hear nothing but cosmic static. The paradox becomes even sharper when you consider time. The universe has been around for 13.8 billion years, plenty of opportunity for countless civilizations to rise, expand, and leave their mark. So why does it feel like we're alone in the dark? One eerie possibility is the zoo hypothesis, the idea that advanced civilizations might be deliberately avoiding us, treating Earth like some galactic nature preserve. Picture an interstellar prime directive, where species far beyond our technological grasp observe from a distance, unwilling to interfere until we reach some unseen threshold. It's a comforting thought in some ways, suggesting we're not abandoned but protected. But it also raises unsettling questions. Who gets to decide when a species is ready? And what happens if we never pass their test? Then there's the darker alternative, the Great Filter. This theory suggests some catastrophic bottleneck prevents life from advancing to interstellar scales, whether it's self-destruction through war or environmental collapse, or some universal hurdle we haven't yet encountered. If the filter lies ahead of us, humanity's future might be far bleaker than we imagine. But if it's behind us, if the leap from chemistry to biology is astronomically rare, then we might truly be the first, or even the only, civilization in our cosmic neighborhood. But here's the twist. An infinite universe doesn't just multiply the possibilities, it stretches them beyond comprehension. Even if intelligent life is vanishingly rare, infinity guarantees it exists somewhere. The catch: distances could be so vast and civilizations so fleeting that overlap becomes statistically impossible. Imagine two fireflies blinking in a continent-sized forest, their flashes separated by centuries. They're out there, but they'll never know each other, which brings us back to us. In an infinite cosmos, humanity isn't special, just one spark in an endless sea of time and space. But that very scale makes our existence astonishing. Against impossible odds, we're here, asking these questions, reaching out to the void. Whether we're alone or not, the universe has given us something precious, the chance to explore, to wonder, and to keep searching for answers in the great, silent dark. In the grand theater of the cosmos, humanity occupies a stage so small it defies comprehension. That iconic pale blue dot image Earth as a single pixel in the vastness of space captures our staggering insignificance. Our entire history, every war and wonder, every triumph and tragedy, unfolded on a speck of dust suspended in a sunbeam. Yet here's the astonishing paradox. This tiny vantage point has given rise to minds capable of measuring galactic superclusters, decoding the birth cries of the universe, and daring to ask what lies beyond the limits of sight. We are simultaneously nothing and everything, cosmic ephemera made of star stuff that has learned to contemplate its own origins. Carl Sagan's famous words echo through this revelation. We are a way for the cosmos to know itself. Every atom in our bodies was forged in the hearts of ancient stars, scattered across space by supernova, and reassembled by gravity's patient hand. The iron in our blood, the calcium in our bones, these are literal pieces of the universe examining its own blueprint. This connection transforms our apparent smallness into something profound. Yes, we're dwarfed by 100 billion galaxies, but we're also the universe's rare chance to witness its own majesty. This duality sparks both humility and hunger. When we peer through telescopes at galaxies millions of light years away, we're not just collecting data, we're time travelers, archaeologists of the cosmos. Each photon that reaches our instruments is a message from eras when Earth didn't exist, carrying secrets from epochs we'll never physically touch. The sheer scale of what we can't see, regions receding faster than light, can bridge the gap might feel like a prison. But it's also an endless frontier, whispering that there will always be more to discover, more mysteries to unravel. Which raises the tantalizing question, could we ever break free from these observational chains? Future civilizations might develop technologies we can't yet imagine: wormholes folding space-time, quantum entanglement networks transmitting data instantaneously, or sensors detecting dimensions beyond our perception. Or perhaps we'll uncover that the ultimate truth lies not in reaching farther, but in seeing deeper, recognizing that the universe's grandest secrets might be hidden in plain sight, encoded in the fabric of reality itself. For now, we stand at this extraordinary crossroads, small enough to vanish in the cosmic background, yet endowed with the singular ability to map our own insignificance. It's a perspective that doesn't diminish us but liberates us, because in a universe so vast, the mere fact that we can ask, "What's out there?" is nothing short of miraculous. The James Webb Space Telescope was just the beginning. This engineering marvel, peering deeper into the infrared spectrum than ever before, has already shattered our cosmic horizons, but the next generation of tools will rewrite the rules entirely. Picture gravitational wave observatories 100 times more sensitive than LIGO, catching whispers of black hole collisions from the universe's first second. Imagine quantum sensors so precise they could detect the gravitational pull of a single atom, mapping hidden masses, warping space itself. These aren't sci-fi dreams, they're blueprints in labs right now, each promising to peel back another layer of the cosmic onion. Dark matter, the invisible scaffold holding galaxies together, might become our next lens. Though it doesn't emit light, its gravitational fingerprints could reveal structures beyond our observational bubble. Scientists are already designing detectors to track its subtle tugs on stars and gas, like cosmic seismographs listening for tremors in the dark. Neutrinos, those ghostly particles streaming through your body at near light speed, offer another backdoor. Future observatories might decode their paths to unveil cataclysms hidden behind the curtain of spacetime, supernova in unobservable galaxies, or even exotic physics at the universe's edge. Then there are the wild cards. Wormhole telescopes sound like fantasy, but if Einstein-Rosen bridges exist, they could funnel light from unimaginable distances without breaking relativity's speed limit. Quantum entanglement, that spooky connection between particles, might one day let us read photons from regions whose light hasn't reached us yet, like tapping into a cosmic Wi-Fi signal from beyond the horizon. These ideas dance at the edge of known physics, but so did black holes a century ago. Yet for all our ingenuity, hard limits loom. The accelerating expansion of space may forever quarantine regions of the cosmos, their light outpaced by the stretching void. Some truths might be fundamentally unknowable, locked beyond a horizon not of distance but of physics itself. It's a humbling reminder the universe owes us no answers. But that's what makes the quest so exhilarating. Every tool we build, every theory we test, is a lantern held against the dark, illuminating not just the cosmos, but the limits of our own curiosity. There's a chilling possibility lurking at the edge of cosmology, that some truths about our universe aren't just unknown, but fundamentally unknowable. Picture a ship sailing toward a horizon that retreats faster than the vessel can move. That's humanity's plight in an accelerating cosmos. The Hubble volume, the spherical region where space expands slower than light speed, isn't just a boundary, it's a prison of perception. Every second, galaxies cross this threshold, vanishing from our future view as their light loses the battle against stretching space. They don't disappear, they become unseeable, like words fading from a cosmic manuscript we'll never fully read. Plato's ancient allegory of the cave feels unnervingly relevant here. We're the shackled prisoners mistaking shadows on the wall, the flickering images of galaxies within our Hubble volume for the entirety of reality. The true cosmos might be an unfathomably vast landscape bathed in sunlight, while we strain to interpret its grandeur through faint silhouettes. Worse still, our cave is shrinking. As dark energy tightens its grip, accelerating expansion will eventually leave even nearby galaxies outside our observational reach. Future astronomers might peer into telescopes to find only blackness, unaware that trillions of stars still blaze beyond their perception. This raises profound ethical questions. Should we pour resources into studying realms that might forever elude detection? Or is the pursuit itself valuable, regardless of answers? History suggests that every unknowable frontier, from the atom to the edge of the solar system, has eventually yielded to human ingenuity. But cosmic expansion operates by different rules. It's not a lack of technology holding us back, it's the laws of physics themselves. The universe seems to be erecting impenetrable walls, not out of malice, but as a consequence of its own explosive birth. Yet here's the paradox: even as the observable universe shrinks in relative terms, our understanding of its mechanics grows. We've deduced dark energy's existence, mapped the cosmic microwave background's whispers, and reconstructed 8 billion years of cosmic evolution, all from within our tiny pocket of visibility. It's as if a prisoner, never leaving their cell, could accurately describe the entire prison's architecture by studying the cracks in the walls, which forces us to confront the ultimate question: does the universe even have an end in any meaningful sense? If space stretches infinitely, the word edge becomes meaningless. If it's finite but unbounded, like the surface of a balloon, the concept collapses too. Perhaps the only true boundary is the one we carry within the limit of what light, time, and the laws of physics allow us to perceive. And that might be the most humbling revelation of all. The universe isn't hiding its secrets. It's simply too vast to ever fully reveal them. We've been asking the wrong question. The universe doesn't have an end in the way we instinctively picture it. No great cosmic wall, no abrupt void where existence stops. Instead, what we call the edge is just a limit of perception, like an ant crawling on a balloon who mistakes its curved horizon for the boundary of all things. The ant's world seems flat and finite, but that's an illusion of scale. Step back, and you'd see the balloon's surface stretches endlessly in every direction, with no true edges at all. Our cosmic horizon works the same way. Those 93 billion light-years we can observe, they're not the universe's final frontier, just the farthest light that's had time to reach us. The real cosmos likely extends much farther, possibly infinitely, with galaxies upon galaxies forever hidden by the relentless expansion of space. Language traps us here. Words like edge and end carry terrestrial baggage. They imply boundaries we can touch or cross, like the rim of a canyon or the shore of an ocean. But the universe doesn't play by those rules. Space isn't expanding into anything. It's stretching itself, creating more distance between points without needing an outside to grow into. Imagine drawing dots on a rubber band and stretching it. The dots move apart not because they're traveling across the band, but because the band itself is elongating. Now picture that rubber band extending forever in all directions with no endpoints. That's closer to how cosmic expansion really works. A process without edges, where the only limits are those of our own vantage point. Cultures across history have grappled with this paradox in fascinating ways. Norse mythology envisioned the cosmos as Yggdrasil, a vast tree whose branches held realms like Asgard and Midgard with no ultimate end, just layers of reality spiraling outward. Hindu cosmology describes the universe as cyclical, breathing in and out over eons, where endings are merely preludes to new beginnings. Even modern sci-fi wrestles with the idea, from the fractal worlds of Interstellar to the cosmic ocean of Arrival, where alien languages reshape human perception of time and space. These stories reveal a profound truth. How we frame the universe's limits says more about us than about the cosmos itself. So what happens if we strip away the metaphors and face the raw physics? The universe might be infinite, curving back on itself like a higher dimensional sphere, or even branching into multiverses we'll never witness. But one thing's certain, the edge we talk about isn't out there in the stars. It's in the limits of our tools, our language, and our imagination. And that's the real frontier waiting to be crossed. Long before telescopes or satellites, humanity stared into the night sky and spun stories to explain the unfathomable. The Norse saw the cosmos as Yggdrasil, an immense ash tree whose roots and branches held 9 realms, from the fiery pits of Muspelheim to the icy wastes of Niflheim. This wasn't just fantasy, it was an attempt to map the boundaries of existence, to give shape to the void. The tree had no true edge, just layers of reality spiraling outward, much like our modern understanding of an expanding universe with no definitive end. Half a world away, Hindu cosmology envisioned something even more radical, an endless cycle of creation and destruction, where universes breathed in and out like living things, each lifetime lasting trillions of years. These ancient myths didn't just guess at cosmic scales, they grappled with the same paradoxes that keep physicists awake today. How can something have no edge? How does time begin or end? What's startling is how these stories prefigured modern science. The Hindu concept of cyclical universes mirrors theories like conformal cyclic cosmology, where the end of one universe seeds the beginning of another. The Norse idea of layered realms finds eerie echoes in the multiverse hypothesis, where separate bubbles of reality float in a grand cosmic foam. Even the Aboriginal Dreamtime, with its timeless, interconnected landscape, resonates with quantum theories where past, present, and future coexist. These weren't primitive fantasies, they were humanity's first cosmological models, built not with equations but with metaphors that stretched the imagination to its limits. Myths did more than explain, they comforted. Faced with an infinite, impersonal cosmos, our ancestors crafted narratives where boundaries, even symbolic ones, made the universe feel navigable. The Babylonian world turtle, the Chinese pillar of heaven, the Greek Titan Atlas holding up the sky, all were attempts to put walls around the infinite. Yet buried in these tales was a truth science would later confirm. The universe refuses to be contained. Just as Yggdrasil's branches reached beyond comprehension, our observable horizon keeps receding, revealing not an edge but more questions. This dance between myth and measurement continues today. The James Webb Space Telescope's deep field images don't just show galaxies. They evoke the same awe that inspired the Navajo to speak of celestial beadwork woven by the gods. Dark energy's relentless push outward feels like a scientific retelling of the Maori myth, where the sky father Rangi is forever separated from the earth mother Papa. The stories change, but the wonder remains a testament to humanity's unshakable need to find meaning in the vast unknown. Yet for all their wisdom, myths couldn't predict the strangest twist, that the universe's true nature might be stranger than any story. As we peel back the layers of cosmic microwave background radiation or chart the large-scale structure of galaxies, we're not just collecting data, we're writing the next chapter in humanity's oldest epic. The tools have changed, but the quest remains the same, to stand at the edge of understanding and peer into the dark and what waits beyond that edge. That's where the hard science gets even more unbelievable. In 2008, astronomers noticed something that shouldn't exist. Giant clusters of galaxies, thousands of them, were streaming through space in the same direction at staggering speeds, as if pulled by some invisible hand. This wasn't random motion, it was a coordinated march toward a point beyond the edge of our observable universe. They called it dark flow, and it remains one of cosmology's most tantalizing enigmas. Think of it like leaves floating down a river, except there's no visible current, no source of the pull, just the eerie certainty that something massive lurks in the unseen darkness beyond. The numbers defy expectations. These clusters are racing at nearly 2 million miles per hour toward a region in the constellations Centaurus and Hydra, a motion that can't be explained by the gravitational pull of any known structure. The sheer scale of this movement suggests an unfathomable concentration of mass, perhaps a supercluster of galaxies so colossal it dwarfs anything in our visible cosmos, or even the gravitational tug of another universe brushing against our own in the multiverse foam. Either possibility rewrites our understanding of cosmic boundaries. It's as if we're ants on a picnic blanket, suddenly feeling the breeze of a passing elephant we can't see. But dark flow is controversial. Some scientists argue it's a statistical fluke, an illusion created by the way we measure cosmic microwave background radiation. Others point to subtle errors in data processing that might amplify false patterns. Yet multiple studies, including analyses of X-ray galaxy clusters, keep reinforcing the anomaly. The debate rages because the stakes are so high. If dark flow is real, it means our universe isn't just larger than we observe. It's asymmetrical, shaped by forces from realms we'll never directly witness. This raises a deeper question about cosmic topology. Could the universe's shape, whether flat, closed like a sphere, or twisted like a pretzel, explain these mysterious motions? If space curves back on itself in higher dimensions, what we perceive as a flow might be light and matter following invisible folds in reality. Imagine a hamster running in a wheel. From its perspective, it's moving forward endlessly, but from outside, the path loops back. Could dark flow be a similar illusion, hinting at a universe far more intricately connected than we've dared to assume? The search for answers is pushing telescopes and supercomputers to their limits. Every new map of galaxy motions, every refinement of the cosmic microwave background, brings us closer to knowing whether dark flow is a key to the universe's hidden architecture or just a cosmic mirage. Either way, it's a reminder that the cosmos refuses to play by the rules we've written for it. Beyond the edge of our vision, the universe might be whispering secrets in a language we're only beginning to decipher. The shape of the universe isn't just about size, it's about the very fabric of reality bending in ways that defy everyday intuition. Picture space not as an empty stage where galaxies move, but as the stage itself, capable of stretching, twisting, or even folding back on itself like an origami sculpture. Scientists describe three possible geometries for this cosmic fabric: flat like a sheet of paper, positively curved like a sphere, or negatively curved like a saddle. Each shape carries mind-bending implications. A flat universe suggests infinite expanse, where parallel lines stay perfectly parallel across billions of light years. A spherical universe, though finite, would have no edges, just as a traveler on Earth can circle the globe endlessly without falling off. And a hyperbolic universe. That's where things get truly bizarre, with space flaring outward in a fractal-like sprawl where parallel lines rapidly diverge. The cosmic microwave background holds crucial clues. Its near-perfect flatness, observed with staggering precision, hints that our universe's geometry is balanced on a knife's edge. If the density of matter and energy were slightly higher, space would curve inward like a ball. Slightly lower, and it would splay outward like a trumpet's bell. Yet the measurements align almost exactly with the critical density needed for flatness, as if the universe fine-tuned itself to avoid dramatic curvature. But here's the catch: flatness doesn't necessarily mean infinite. Just as a sheet of paper can be rolled into a cylinder, flat locally but finite globally, our universe might have hidden topological tricks. This is where the video game analogy clicks. Imagine an old-school arcade racer where driving off the right side of the screen teleports you to the left, a seamless, wrap-around world with no true edges. The universe could function similarly, but in 3 dimensions. Astronomers call this the dodecahedral space model, where the cosmos repeats like a hall of mirrors, allowing light to loop back on itself over vast distances. If true, we might someday spot duplicate galaxy clusters, ghostly echoes of the same structures appearing in multiple directions. Now, take this a step further. If the universe can curve or loop, could it also collide with others? Some theories suggest our cosmic bubble might have bumped into neighboring ones in the multiverse foam, leaving bruises in the cosmic microwave background. Others propose that the Big Bang itself was the aftermath of such a collision, a shattering impact that birthed our reality from the wreckage of a higher dimensional crash. The shape of our universe, then, isn't just a static fact, it's a dynamic fingerprint, a clue to forces and realms beyond our current grasp. What if the cosmic microwave background isn't just a relic of our universe's birth, but a scar from a violent encounter with another reality? The idea sounds like science fiction, but physicists take it seriously. When our universe was a mere fraction of a second old, still bubbling with the energy of inflation, it might have brushed against a neighboring bubble universe, a separate cosmic domain with its own physics, its own history. Such a collision wouldn't have been a cataclysmic crash, but a subtle gravitational nudge, leaving faint ripples in the fabric of space-time. These ripples would imprint themselves on the cosmic microwave background like fingerprints on glass, a ghostly signature of a realm we can never directly observe. The search for these imprints has zeroed in on a bizarre anomaly nicknamed the axis of evil. This puzzling pattern in the CMB shows unexpected temperature alignments, as if the universe has a preferred direction, violating the long-held assumption that the cosmos is uniform in all directions. Some researchers argue this could be evidence of a collision with another universe, a cosmic fender bender that left our reality slightly dented. Others propose less exotic explanations, like statistical flukes or instrumental errors. But if the signal is real, it could be our first tangible clue that we're not alone in the multiverse. Imagine two soap bubbles floating in a sink, briefly touching before drifting apart. The point of contact leaves a faint mark, an echo of something vast and unseen. Testing this theory pushes science to its limits. If bubble universes exist, they're forever beyond our observational horizon, their light unable to reach us across the expanding gulf of space. All we can do is study the aftermath, the cosmic equivalent of detectives reconstructing a crime scene from a single smudged fingerprint. Some models suggest these collisions would create distinct, circular patterns in the CMB, like concentric rings of altered temperature. Others predict bizarre gravitational lensing effects, where light from distant galaxies bends in unexpected ways. The challenge is separating these signals from the noise of a 13.8 billion-year-old universe filled with supernova, black holes, and dark matter's invisible pull. This pursuit forces us to confront the fragility of our scientific models. Physics thrives on predictability equations that describe how stars shine, how particles collide, how space curves. But when it comes to the multiverse, we're groping in the dark. Our theories might be like a fish trying to understand rain, limited by the pond it swims in, unable to grasp the vast sky above. The axis of evil could be a flaw in our measurements, a quirk of statistics, or the first crack in a much larger cosmic puzzle. Either way, it's a reminder that the universe owes us no clarity, and that the most profound discoveries often begin with anomalies that refuse to fit the rules. Which raises a humbling thought. What if the multiverse isn't just untestable, but unimaginable? Our brains evolved to navigate a world of medium-sized objects moving at medium speeds, not to comprehend higher dimensional collisions or infinite bubble universes. The true nature of reality might be as alien to us as a symphony is to a bacterium, vibrating in ways we lack the senses to perceive. Yet here we are, piecing together clues from the faintest whispers of radiation, daring to map the unseeable. That's the paradox of cosmology. The closer we look, the more the universe reveals how much we've yet to understand. Even our most brilliant scientific theories have limits, frontiers where the rules break down and the equations dissolve into chaos. Picture a 16th century map, its edges adorned with the chilling warning, "Here be dragons." That's where cosmology stands today, staring into the abyss where general relativity and quantum mechanics, the twin pillars of modern physics, clash violently. Einstein's masterpiece describes gravity as the curvature of spacetime, weaving the cosmic dance of planets and black holes with breathtaking precision. Yet at the quantum scale, where particles flicker in and out of existence, relativity's elegant fabric frays into nonsense. Black holes embody this crisis perfectly. Their immense gravity warps spacetime like a bowling ball on a trampoline, but their cores crush matter into a singularity, a point so infinitely dense that the laws of physics simply give up. It's like trying to navigate a ship with two flawless yet contradictory maps, one for the open ocean, the other for uncharted storms. This isn't just academic frustration, it's a glaring signpost that we're missing something profound. To unite these warring theories, physicists chase the holy grail of quantum gravity, a framework where spacetime itself dissolves into probabilistic foam at the smallest scales. String theory suggests reality is built from vibrating threads a billionth of a billionth the size of an atom. Loop quantum gravity imagines space as a network of interconnected rings. Even wilder ideas like holographic duality propose that our three-dimensional universe is a projection from a two-dimensional surface, like a cosmic illusion. These aren't just tweaks to existing models, they're radical rewrites of reality's rulebook, yet the dragons at the edge of our understanding guard deeper mysteries. Could consciousness, the very act of observation, play a role in shaping cosmic boundaries? Quantum mechanics already blurs the line between observer and observed, suggesting particles exist in superposition until measured. If perception influences the quantum realm, might it also echo across the vast scales of the universe? It's a controversial idea, but one that forces us to confront whether the ultimate frontier isn't just out there in the stars, but woven into the fabric of awareness itself. The search for answers isn't just about filling textbooks, it's about humility. Every time our models fail, the universe reminds us that reality is stranger than our boldest theories. And that's where the real adventure begins. Does the universe exist in a definite state, or does it crystallize into reality only when observed? This isn't just philosophy. Quantum mechanics forces the question. At the smallest scales, particles exist in a haze of probabilities until measured, as if the act of observation pins them to a single point. Now stretch that idea to cosmic proportions. What if the universe itself, with its galaxies and voids, depends on observers to snap it into focus? The thought is dizzying. A cosmos where the boundaries of reality shift with the gaze of conscious beings, where the edge of the observable universe isn't just a limit of light, but a limit of perception. The anthropic principle sharpens this paradox. It suggests we observe a universe finely tuned for life because, well, we're here to observe it. If the constants of nature, gravity's strength, the mass of electrons deviated even slightly, stars wouldn't form, chemistry would fail, and life would be impossible. So is our universe one lucky roll of the dice in a multiverse casino? Or does consciousness somehow retroactively select for the conditions that allow it to exist? The answers teeter between physics and metaphysics, challenging us to consider whether the cosmos is a pre-written script or an improvisation shaped by its audience. Lee Smolin's cosmological natural selection offers a radical twist. Imagine black holes as cosmic wombs, birthing new universes with slightly tweaked physical laws. Over eons, universes that produce more black holes better at replication would dominate the multiverse landscape. In this Darwinian cosmos, fine-tuning isn't luck, it's evolutionary inevitability. Our universe's life-friendly constants might simply be the ones that favored prolific black hole production, with life as an accidental byproduct. It's a stark contrast to observer-driven theories, replacing consciousness with cold, mechanical selection. Yet these ideas all circle back to the same profound mystery. The observable universe's horizon isn't just a barrier to knowledge, it's a mirror, reflecting how deeply our understanding of reality is entangled with the act of observation. Whether shaped by consciousness, selection, or sheer chance, the cosmos we perceive is filtered through the narrow keyhole of our existence, and that raises an unsettling possibility. The true universe, unfiltered and unobserved, might be stranger than we can fathom, a shadow play waiting for witnesses to give it form. The so-called edge of the observable universe isn't a wall or a cliff. It's a horizon of understanding, a shifting border between what we've decoded and what still lies shrouded in the unknown. Think of it like standing on a mountain ridge at dawn, watching distant peaks emerge from the mist as sunlight creeps forward. Those mountains were always there. Your ability to see them simply depended on the light's journey. Our cosmic horizon works the same way. It doesn't mark where reality ends, but where our vision, bound by the speed of light and the age of the universe, temporarily falters. Contrast this with boundaries we can physically encounter, like Earth's atmosphere. At the Kármán line, 62 miles up, the sky doesn't abruptly end, it thins until molecules are too sparse for wings to grip. Yet we can cross it, measure it, feel its gradual fade. Even a black hole's event horizon, that infamous point of no return, has tangible effects: spaghettification, time dilation, Hawking radiation. But the cosmic horizon, it's a limit woven into the fabric of space-time itself, not by gravity or matter, but by the simple fact that the universe hasn't existed long enough for more distant light to reach us. This distinction reveals a humbling truth. Science isn't just about pushing boundaries, it's about realizing how many boundaries are illusions of perspective. Every time we build a better telescope or a more sensitive detector, that horizon rolls back like a retreating tide, exposing new realms of stars and galaxies that were always there, waiting for their light to finally arrive. The real frontier isn't a place, it's the gap between what the universe has revealed and what it still holds in shadow. What makes this mystery so electrifying is that the answers may defy not just our technology, but our very capacity to imagine. The true nature of the cosmos could be as incomprehensible to us as a smartphone would be to a medieval farmer, not because we lack intelligence, but because reality operates on rules we've yet to uncover. Perhaps space is knotted in higher dimensions, or our universe is a hologram projected from some distant boundary. Maybe beyond isn't even the right word, and the totality of existence makes our observable bubble seem as insignificant as a single atom in a cathedral. That's the thrilling paradox of cosmology. The more we learn, the vaster the unknown becomes. Each discovery unfurls new questions, stretching our minds to grasp concepts that feel more like poetry than physics. Yet this endless pursuit isn't discouraging, it's liberating. It means the universe will always have secrets to whisper, always have wonders to unveil. So when you next look up at the night sky, remember, those pinpricks of light aren't just stars. They're invitations to a journey without end, a reminder that the greatest adventure lies not in reaching the edge, but in realizing there isn't one. So where does this leave us staring at the night sky? We now understand that the cosmic horizon isn't a boundary, it's a starting line. Every star, every galaxy, every flicker of light we detect is just the nearest ripple in an ocean whose depths stretch beyond imagination. The observable universe's edge isn't a wall, it's a time-stamped postcard, a fleeting glimpse of a reality that's already grown vaster since the light began its journey to us. This realization is equal parts humbling and exhilarating. Humbling because it shatters any illusion that we're at the center of something finite. Exhilarating because it means the cosmos is a story still being written, with chapters we've yet to read. Theoretical physicist Janna Levin once said, "The universe is under no obligation to make sense to us." That's the beauty of it. The more we learn, the more we're confronted with questions that defy intuition. A dark flow pulling galaxies toward the unseen, bubble universes brushing against ours in higher dimensions, the possibility that our entire reality is one pixel in an infinite mosaic. These aren't flaws in our understanding, they're invitations to dig deeper, to stay curious. After all, if everything made sense right away, where would the wonder be? That's why this journey doesn't end here. Every new telescope, every breakthrough in quantum gravity, every flicker of data from the cosmic microwave background peels back another layer of the mystery. Maybe you're someone who looks up at the stars and feels small, or maybe you're the kind of person who leans in, itching to know what's really out there. Wherever you land, remember, the universe doesn't owe us answers, but it does offer us the chance to keep asking. So what do you think lies beyond the horizon? Another universe, infinite repetitions of our own, or something so strange we haven't even dreamed it yet? Drop your wildest theories in the comments. I read every single one. And if you're ready to keep unraveling cosmic mysteries with me, hit subscribe, because trust me, we've only scratched the surface. The universe is waiting, and its greatest secrets are still hiding in the